a lot of things, a lot of concepts we're going to talk about. In this exact video, we want to talk about the same mechanism, right? About 2,3 BPG. And I want to introduce a concept called the right shift, okay? So that's the concept, right shift. Now you will see this in a lot of questions, right? So 2,3 BPG and oxygen hemoglobin dissociation curve. So we're going to learn about this dissociation curve, right? We are basically studying that how the O2, the oxygen, gets deloaded, right? And why we see a right shift in the curve. Okay, that's the whole theme of this video. So let's start with basic thing, right? Let's just forget about everything first of all, and I'm gonna ask you guys to close your eyes and let's imagine you own a delivery company. Okay, you own some Amazon delivery company. Now you have trucks, a lot of trucks, and your trucks carry packages, right? And what is truck's job? Is it to hold the package forever, or the job is to pick up the package and deliver them, right? I think that's the job, right? It's not to hold the package forever. You're not a warehouse. That's the job of a warehouse, right? So that's exactly what hemoglobin is. That truck is hemoglobin. Now, what is hemoglobin, right? What is HP? What is hemoglobin? Now, hemoglobin, it's like something that carries oxygen, yeah. But okay, let's understand it more fundamentally. Hemoglobin is a protein, first of all. In nature, what is it? It's a protein. Now, where is it found? It's found inside the RBC, okay? It is found inside red blood cells, yes. So, how many oxygen molecules can one hemoglobin carry? What do you think? The answer is 4. We can carry around 4 oxygen molecule. Why is that? Because we have 4 heme groups, okay? Because hemoglobin has 4 heme group. Now each heme group contains 1 ferrous iron, okay? So we have 4 heme group, right? Let me make it. Okay, so we have 4 heme group. This is heme group number 1, this is heme group number 2, the heme group number 3, and the heme group number 4, right? We have these 4 of them. And each heme group has a ferrous to it, okay? Each heme has a ferrous, Fe2 plus, right? Each one has one. That's important. Fe2 plus, Fe2 plus, Fe2 plus, and Fe2 plus. So that's the thing. The thing is that each ferrous binds to 1 oxygen here now. O2, 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 and O2. So we have like 4 seats for oxygen. Okay, that's the answer why we have 4 seats for the oxygen, right? So one hemoglobin, that is one hemoglobin, okay? One hemoglobin has 1, 2, 3, and 4 heme groups. In 4 heme groups, we have 4 iron atoms. 1, 2, right? Right, I hope you can see that, right? 1, 2, 3, 4. And then each ferrous has 1 oxygen molecule, okay? So next question, why doesn't the oxygen simply dissolve in water? That's a cool question, I think, right? Because oxygen is quite soluble, right? So of course oxygen dissolves in water, right? Oxygen dissolves in blood because plasma is just water, right? Your blood is just water, right? So the thing that happens is that around 99%, like I think 99%, it binds to the hemoglobin, HP, but 1% gets dissolved in the plasma, okay? So that's what happened. So 1% is in plasma, okay? I'm building these things, right? So without hemoglobin, you will not have this 99%. That's very important, right? And you'll be surprised that we have literally quite similar protein structure of chlorophyll and hemoglobin. It's just the color is different, okay? Okay, so let's start with hemoglobin, okay? Let's go to the journey of hemoglobin. We are hemoglobin right now. Close your eyes and just listen to me, right? So let's follow one hemoglobin or be one hemoglobin, right? Now, the first stop that we are gonna be at is lungs. We're gonna go and we're gonna pick up that oxygen, right? So because what, how, right? We're gonna pick up that oxygen, right? Goes to the lungs. Oxygen concentration is high there, so hemoglobin lowers that oxygen. Then it goes to the circulation, right? Then we have systemic circulation. So systemic system, right? So we have systemic circulation. It travels there, right? In the blood, RBC travels, and then it goes to the target tissue or muscle, whatever you want to call it. So it leads to the tissue, right? And there at the tissue and the muscle, the hemoglobin unloads the oxygen, right? Now the question there in the tissue is that should the hemoglobin hold the tissue, hold the oxygen tightly or not, right? Of course not. The answer is not, right? Because you want to release that oxygen. For what are you even carrying it for if you don't want to release it, right? Now the problem here is that how does the hemoglobin knows that oh, I'm in the lungs, oh, I'm in the tissue, right? Because I really tried to understand that, and really, when I was in my med school, I mean, I just graduated like 1 month ago, but when I was in third year or maybe second year of my med school, and I mean, at that time, first year, really the internet was, I mean, it was nice, yeah, but it was nice for Instagram and this social. It was not so nice for studying, right? But because you have to search each and every fact, and it took me hours honestly to search a particular answer. So it was a big problem. Now it's not such a big problem, right? That's how I can really teach and learn uninterruptedly, right? That's how I can really, because it's much better now, trust me. Learning is just way easier now. So the problem here with the hemoglobin is that hemoglobin doesn't know that if it's in the lung, if it's, because it doesn't have its own brain, right? It cannot think. Instead, what happens is that it depends upon the local environment, right? It depends, because in lungs we have high concentration of what? Of oxygen. In tissue we have low concentration of oxygen. Okay, so that's how the hemoglobin understands that, hey, I have to drop that now. Okay, I have to drop that oxygen, right? So this is exactly nice. This is the exact moment that where I want to introduce you to the new concept. The new concept is oxygen dissociation curve, right? Now I'm gonna put this concept in you. Now we're gonna study the curve, right? So what is this curve, right? Now we're gonna study that. Now, what exactly is that curve? Okay, curve is just, we put some x-axis and y-axis, and we just put a point, and we are trying to understand the behavior of hemoglobin. That's the dissociation curve. Now, by dissociation, we are trying to understand that how come that hemoglobin can unload the can just unload that oxygen, right, in that environment of tissues. We just trying to understand the dissociation, okay, simply. So we have that curve. Now on the x-axis, I'm going to make this x-axis, right? That's the x-axis. And here I'm going to make this, what is this x-axis? X-axis here is partial pressure of the oxygen. So that is PO2. Now, a lot of you guys don't really know the meaning. Exactly, partial pressure of oxygen means how much oxygen is available. That's it, right? So how much O2 is there, okay? And on the y-axis, right? That's a y-axis, right? And here I'm going to put saturation of a hemoglobin, how saturated a HB is, right? So just I'm gonna write it as saturation, okay? Saturation, and how saturated the hemoglobin is. By saturation I mean how many seats of ferrous are filled by O2, okay? That's the thing. How many oxygen binding sites are occupied, in other ways, right? So the question here is, if PO2, that's the partial pressure, right, which is availability of oxygen, right, which is in the lung, right? If the availability increases, if the graph goes there this side, what happens to the hemoglobin, right? What happens to does the hemoglobin binds more oxygen or not, right? So when you increase the PO2, when you increase this, when you increase the amount of oxygen in an environment where I put this hemoglobin, right, what happens is that hemoglobin will automatically bind more oxygen, right? And the graph will move upward as well, and this way as well, right? The graph will move like this, okay? So that's the one thing, right? So a lot of people will think that it's not a straight line because of cooperativity, right? Now this is a new word, right? Cooperativity. Now what is cooperativity? Let me just put that word in you. Operativity. positivity. Now this concept right there, how would I explain that? I would explain to you by an example. Imagine we have 4 friends, right? Friend number 1, friend number 2, friend number 3, and friend number 4, right? The first friend enters in the room, okay? It goes some in the room, right? Okay, the first friend enters in the room, right? And later on, we find out that nobody like number 2 or number 3 or number 4, nobody wants to enter that room, okay? It's very difficult for them to enter. But after one enters, the other follows easily. Hemoglobin behaves similarly, okay? So when first oxygen binds, the hemoglobin changes its shape. And the thing is that when first binds, right, the hemoglobin changes its shape, and the second oxygen is going to bind easily, and the third even more easily, and the fourth is even more easily. And that's, we call it positive cooperativity, right? That's a positive cooperativity. What is negative cooperativity? Just the vice versa of that. So what is negative cooperativity? It's just that when you have one, right, so one enters in the room, right, and it gets tougher for other people because maybe the room is so small or something like that, okay? I'm trying to just explain that little concept of yours, okay? So one enters, and as soon as one enters, everyone's like, wow, we want to get inside as well, because somehow the structure of the room, or a hemoglobin changes, and it becomes easier for oxygen to bind, right? Now understand this thing. The structure, by structure I mean 2 state, before binding and after binding, okay? So we have 2 major conformational changes. Let's start with first change. First state is called T state, right? This is called tense. Here I'm going to write this word, tense, right? Now the question here is, what's the affinity for for oxygen here? It's very low, right? Here it's very less. So affinity for glucose is low here, right? Doesn't want oxygen much. It's really easy to release the oxygen here. Release O2 easily, right? And the other state, the other structural state is R state, right? What is R state? Is relaxed. He's relaxed, right? So what's the affinity here? Affinity is high here. It wants to bind, okay? So affinity is high, wants to bind, okay? Wants O2, right? So these are 2 different states of hemoglobin right there, okay? So the question here that rises is that which state dominates in the lungs, because we want to have O2, right? So obviously the R state is gonna dominate in the lungs, right? So that's very obvious. And next question is, which state will dominate in the tissue? Well, it's obvious as well that the state called T state will actually dominate in the tissues, right? So I'm really talking about the structure of hemoglobin right now, right? So that's how the structure of hemoglobin actually changes, right? And so T you can remember as tissue or tense or just like that, and R is just relaxed, so it's in the lungs, right? So let me introduce you to a new character. It's called 2,3 BPG. Now this is the character called 2,3 BPG, right? Now where does it bind to? It doesn't bind to oxygen, does not bind to iron, doesn't bind to heme as well. The thing that 2,3 BPG binds to is, it binds to something which is called as, wait, let me write it. Wait, it's better to write it honestly. So 2,3 BPG actually binds with beta chains of deoxygenated hemoglobin. Now it's very important. What happens after the binding, right? It binds it, right? Now you must be thinking, wow, what are these beta chains, right? So we have a lot of chains, right? Alpha chain, beta chain, gamma chains, and delta chains, right? And we have, I'm not going to go deep into them because I don't want to sidetrack So basically alpha chains, beta chain, and gamma chain and delta chain, these are 4 chains, and you mostly have beta and alpha. And if you have some sort of disease called thalassemia, you won't be able to make beta because of a point mutation, right? And what happens is that the shape of hemoglobin actually gets messed up, and then you will not be able to bind to the oxygen well. So that's what happens in thalassemia, and I'm trying to explain you this concept very fast. Okay, beta chain is just like a supportive chain, right? And alpha chain is also a supportive chain, but you need these chains in your hemoglobin to have a structure. Okay, so what happens when 2,3-BPG? First of all, where does 2,3-BPG even comes from? Well, 2,3-BPG comes from 1,3-BPG, right? And when 1,3-BPG interacts with bisphosphoglycerate mutase, it actually goes under a change where the functional group actually, the phosphate actually changes its position from first carbon to the second carbon, and then we have this product, right? And this first 1,3-BPG comes from glycolysis, and glycolysis happens in RBC because RBCs don't have mitochondria, right? Because if they had mitochondria, they would just use up that particular oxygen that they are carrying, right? So God was like, okay, I'm not gonna make this mistake in my design, and okay, so they don't have the RBCs to waste. So so that's the little story that I just told you about this 2,3-BPG. So let's come back to the main topic, right? So main topic is what happens when 2,3-BPG binds with the beta chains, right? And note that if you have thalassemia, you won't be able to see that binding, right? That's going to be a big problem for you guys. Okay, so what happens after binding? What happens is that as soon as the 2,3-BPG binds with the beta chain, it starts actually stabilizing. It starts stabilizes that T state, okay? So stabilizes the T state, right? Now remember that T state is the state of low affinity. It's the state of tissue, right? So affinity goes down, right? Now if affinity even decreases more, what happens? The hemoglobin lets out the oxygen more easily, right? So this is exactly what tissue needs, right? So now I'm gonna introduce to the right shift, right? Now I have this graph, right? And it's gonna shift to the right. Now here's the thing, right? What actually is shifting, right? The thing is that entire oxygen dissociation graph is shifting, right? Suppose we don't have 2,3-BPG. So hemoglobin is like 95% saturated. Here's the 95%, right? Suppose we don't have that, 2,3-BPG that's supposed to make your hemoglobin drop that oxygen, right? So hemoglobin is 95% saturated at certain PO2. For example, at maybe let's take 80% PO2. I'm just ballparking here, right? So we have this 80% PO2, and our saturation is around 95%, right? So after I add, 2,3-BPG here in this equation, right? What's going to happen is that at the same PO2, at the same partial pressure, the hemoglobin will the saturation will actually drop. It's gonna maybe it's gonna go to 85 now. Okay, so hemoglobin might be now at 85 saturation. Now, where did this missing oxygen actually go? This 10% of oxygen, right? That's the question. It actually went inside the tissue. That's what happened, and this is why oxygen delivery is is improving under the management of 2,3-BPG, right? So that's the concept I was trying to put in, and we see a right shift here. Wait, let me make it a little prettier. Yeah, so why is it called a right shift, right? Because on the graph, right, hemoglobin now requires a higher PO2. This is a higher PO2 to achieve the same level of saturation, because the saturation is dropped under 2,3-BPG, right? So it needs higher PO2 now, right? It is right. So the graph moves towards the right, on the x-axis, right? Because on the right, so you can also remember this as right as release. That's also a good memory hook. Okay, so why would RBC want to do that, right? Imagine you're like running and muscles consume ATP rapidly, so you need oxygen, right? Now, would you prefer hemoglobin to cling to that oxygen, or you want that oxygen to be released immediately inside the tissue? You want that to be released, so that's why RBCs increase the synthesis of 2,3-BPG under load, under some sort of exercising, right? And especially under high altitude. Whenever we climb a mountain, what changes first is atmospheric oxygen falls, the PO2 falls, right? So PO2 actually goes here, not here, I mean, from here it goes to maybe here, right? So the atmospheric oxygen fails. So what happens next is that your blood oxygen also fails, right? And when the blood oxygen fails, the tissue receives less oxygen, right? Now, how does the body compensate for that? The body compensates by actually producing 2,3 BPG more, because now your body knows that, oh shit, we have less oxygen. So I mean, I know that my capability, my affinity towards the oxygen is going to stay the same. I don't have any chemical compound that's going to increase my affinity. I am not gonna somehow pick up 10 molecules of O2 when my capacity is just 4, right? I cannot increase my capacity, so I would rather increase my this delivery of oxygen to the tissue, right? So that's how the adaptation works exactly. So tissue receive, more oxygen, right? So even though blood contains less oxygen, the oxygen that is present is delivered more efficiently, right? Even in chronic anemia, suppose you have hemoglobin that falls from 15 gram deciliter to 8 now, right? You lost a lot of blood somehow, right? And so what's going to happen? Can the body create hemoglobin immediately, like next day? No, of course not. It's going to take weeks, like, to make this, to synthesize that hemoglobin. What's going to happen actually is that your your hemoglobin that is present at that particular time is going to increase that 2,3-BPG synthesis. Now, as soon as the 2,3-BPG synthesized, right, you're going to have much easier time releasing that oxygen to the tissue rather than, just keeping that affinity. That's like brilliant compensation, I think, even under exercising, right? So that's kind of the idea here, right? What about fetal hemoglobin? I mean, let's think about it. What if fetal hemoglobin responds strongly to 2,3-BPG, right? Because we know that fetal hemoglobin has very high affinity towards oxygen, right? Would that be good if we have 2,3-BPG? No, because fetus needs to pull oxygen from maternal blood supply, right? From placenta. And it's very tough to pull that blood from placenta because if 2,3-BPG goes up, you would have less affinity towards oxygen and you wouldn't be able to extract enough oxygen across that placenta, and your fetus gonna have a tough time, right? So fetal hemoglobin is called HbF, by the way. Let me just put it in the words, right? So fetal hemoglobin is called HbF, right? And it binds to, and it will binds to 2,3-BPG actually very poorly. This doesn't have that structural compatibility, right? So HbF has quite high affinity, and actually HbF, on the dissociation curve, we actually see a left shift rather than we see a left shift rather than a right shift. We see right shift on mostly beta chains, right? On adult hemoglobin, right? So this allows the oxygen to be transferred from mother to fetus, this hemoglobin, right? And this is how it actually works. What about carbon monoxide, right? We know that carbon monoxide has higher affinity than oxygen, right? What happens if carbon monoxide binds to hemoglobin? The thing is that carbon monoxide, that CO, right? The CO that is carbon monoxide, right? Carbon monoxide, right? So carbon monoxide binds to iron, that is ferrous 2+, and it has affinity more than 200 times of O2. That's very surprising, but a lot of people don't know that. It's like super duper tough to remove that carbon monoxide. So only fewer oxygen binding sites then be available, right? And it's going to be very tough for the oxygen to get stuck on that hemoglobin, because as soon as the CO binds, we're going to see a left shift, right? So we're going to see severe tissue hypoxia, and we're going to have normal PO2, because your PO2 is just basically the percent of oxygen in the lungs, right? In the blood, not in the lungs exactly, but in the blood. So that's the whole thing, right? So if someone asks you which molecule shifts the oxygen dissociation curve to the right, you want to answer 2,3 BPG. That's a good answer. I think that's a good answer. And if someone asks you which molecule makes your dissociation curve go on the left, I think you can answer carbon monoxide. I think that's a solid answer. Now, suppose we don't have 2,3 BPG, then we're going to have really big problems when it comes to adaptation on pressure, right? Adaptation under pressure, like high altitudes, exercises, right? Anemia, the examples that I just gave you. So that's how it actually works. So just shortly, I want to tell you again, this increase 2,3 BPG leads to decreased affinity for O2. That's a fact right there. And I just explained you everything. What about carbon dioxide? Carbon dioxide also leads to decreased affinity. What about protons, right? This H plus protons, right? It gives the pH, right? It reduces the pH. It also leads to decreased affinity for oxygen. And this is exactly, or even higher temperatures, like you have a fever, even that decreases the affinity for oxygen, right? So all of these things like temperature, carbon dioxide is also acidic in nature. H plus ions, right? That's also acidic in nature. Both of them actually leads to decrease in pH, and that makes your blood acidic. And once your blood is acidic, you'll have less affinity for O2. You're gonna pick up, instead of maybe 4, right? Instead of 4 O2, you're gonna maybe pick up 3 or even 2 or even 1. So that's how you actually get hypoxia in terms of metabolic acidosis, right? So that's it. That's it. This is the title of the video, how 2,3 BPG actually works, right?